molecular shape, and molecular polarity. We understand this in the context of valence shell electron pair repulsion theory. Vsepr theory for short, but we say Vsepr theory, not Vsepr theory. Electrons are negatively charged, and they organize themselves into domains. And the main idea of Vsepr theory is that these domains try to be as far apart as possible in space, given the fact that they are all attached to the central atom. Each of the following counts as exactly one electron domain. A single bond. That's easy since it's one pair of electrons. A double bond is two pairs of electrons, but since it's localized in the same region of space, it's considered one electron domain. Same thing with a triple bond. It's three pairs of electrons that share the same region in space, so it's one electron domain. And a lone pair, even though it's not part of the bonding, it's still a pair of electrons repelling other electron domains. So each of these counts as one electron domain, and you need to be able to count these, because it's the number of electron domains that's really important. In fact, it's the number of electron domains on the central atom that determines the electron geometry of the molecule. Now, the electron geometry is an important step because it's the electron geometry and the number of peripheral atoms that determines the molecular shape. So, the number of electron domains on the central atom is called the steric number. And we can make a table of steric number versus electron geometry. What I'm about to show you, I'll do using this simulation. And I will include a link in the description of this video on YouTube so that you can enter the simulation and follow along. So we're going to start out with a steric number of 2. A steric number of 2 means that our central atom has 2 bonds. It could be 2 single bonds, it could be 2 double bonds. It could be a single bond and a triple bond. Or it could be a triple bond and a lone pair, something like that. The electron geometry will be linear. So I click on the link for my simulation and I go to Model. And you can see right here, this model has a central atom and 2 peripheral atoms, meaning it's got a steric number of 2 because that's 2 bonds. And I can sort of rotate it around. You can see that the molecule can bend a little bit, but those peripheral atoms want to be 180 degrees from each other because this electron domain is repelling this electron domain. You can see here I've replaced a single bond with a triple bond, but again, this bond angle is 180 degrees because the steric number is still 2. And again, you can make the molecule bend a little bit, but it's always going to return to 180 degrees because of electron-electron repulsion. I could replace the bond with a lone pair, and you can see the lone pair still is orienting away from the bonding pair because again, there's electron-electron repulsion between the 2 electron domains. An example of a linear molecule with 0 lone pairs is carbon dioxide. If you go through the steps to draw its Lewis structure, you'll see it looks like this. And we only are concerned with the electron domains on the central atom, so 2 domains, the steric number is 2, and we get a 180 degree bond angle. And here's a picture of a CO2 molecule. The black sphere represents a carbon, and then the 2 red spheres represent your oxygen atoms. Next, let's look at steric number 3. This can mean 3 single bonds, 2 single bonds and 1 double bond, or 2 bonds and 1 lone pair. In any of these 3 cases, your electron geometry is what we call trigonal planar. Here's a model with 1, 2, 3 single bonds, so steric number of 3. And you can see that the peripheral atoms point to the corners of an equilateral triangle. All of the bond angles are 120 degrees. If you look at the molecule from the side, you can see it's flat. That's why we have the name trigonal planar. You can bend the molecule and try to distort it, but it will always return to being flat with bond angles of 120 degrees. I could replace one of my single bonds with a double bond, and you can still see that we get back to a trigonal planar molecule at 120 degrees. I could replace a bond with a lone pair. Let's say I had a double bond and a single bond and a lone pair. Again, this is still a trigonal planar electron geometry with a bond angle of 120 degrees. An example of a trigonal planar molecule is sulfur trioxide. We have drawn the Lewis structure before in a previous video. There's actually 3 resonance structures, and this is one of them. So, you can see 1, 2, 3 electron domains, so the steric number is 3. That's 2 single bonds and 1 double bond. Now, time to point something out in the Lewis structure. This looks like a 90-degree angle, and this looks like a 180-degree angle. So the angles in a Lewis structure do not reflect the actual angles in the molecule, right? Because this is trigonal planar, so the actual bond angles will not be 90 and 180, they will all be 120. Lewis structures have right angles, that's just the way you draw them, but they don't necessarily reflect reality. So here's a nice little picture of what our sulfur trioxide molecule might look like, with the purple atom representing sulfur and the 3 white ones representing oxygen. On to steric number of 4. Steric number of 4 can mean 4 single bonds, 3 single bonds and 1 lone pair, or 2 sigma bonds and 2 lone pairs. Regardless of what the combination is, if the steric number is 4, the electron geometry will be tetrahedral. An example of a tetrahedral molecule would be methane, CH4. So there's the Lewis structure for methane. It has 8 valence electrons that are all consumed by making the skeleton. And it looks like all of the bond angles are 90 degrees, right? But that's the lie of the Lewis structure. Remember, a Lewis structure is a 2-dimensional representation of a molecule, which is a 3-dimensional object. And the geometry is determined by the fact that the 4 electron domains are repelling each other and they're trying to get as far apart as possible. So is it possible to have 4 domains further apart from each other than 90 degrees? Well, it isn't in 2 dimensions, but it is in 3 dimensions. Back to the molecular modeling simulation. Here's your central atom, which could be your carbon if we were talking about CH4, and your 4 peripheral atoms, 1, 2, 3, 4. Now, from this angle, it almost looks like these bond angles could be 90 degrees, right? But if I click on the thing to show bond angles, it's actually 109.5. And if we rotate the molecule, then you can see that it is not like a square at all in any way. In fact, it's more like a tetrahedron. So imagine that this, and this atom are all connected to each other, making the base of a pyramid, and then the central atom is at the center of mass of that pyramid, and then this atom is at the top of the pyramid, the apex. That's what it means to be tetrahedral. Right, so that's a tetrahedral electron domain geometry. And let me replace one of the bonds with a lone pair. You can see I still have my 3 peripheral atoms at the base of the pyramid. Holy cow. Just like we had before. And now the lone pair is pointing to the apex of the pyramid. And I can replace one of those single bonds with another lone pair. Now the bond angle is still 109.5 degrees. And the electron domains, whether they're bonds or lone pairs, are still pointing to the corners of the pyramid. So now I've added a nice picture of what our tetrahedral molecule should look like to our table. Bear in mind these angles are 109.5 degrees, all of them. And these peripheral atoms point to the corners of a tetrahedron, right? So if you imagine this as a 4-sided pyramid, that's what it looks like. So let's add another column to our table for molecular shape. When a molecule with linear electron geometry has 0 lone pairs, that means it has 2 peripheral atoms. Just as in this CO2 molecule shown here. That means the molecular shape is linear. In trigonal planar electron geometry, if you have 0 lone pairs, that means you have 3 peripheral atoms, and your electron geometry is trigonal planar. If you have 1 lone pair, that means you have 2 bonds and hence 2 peripheral atoms, and so your molecular shape is bent. In tetrahedral electron geometry, if you have 0 lone pairs, that's 4 peripheral atoms, and your molecular shape is the same as your electron geometry. And this is always the case when you have 0 lone pairs. But in the case of 4 electron domains, none of which are lone pairs, the molecular shape is tetrahedral. If you have 1 lone pair and 3 peripheral atoms, then we call the molecular shape trigonal pyramidal. So it's just like replacing the atom at the apex here with a lone pair. So the central atom is actually at the top of a shallow pyramid with 3 sides. If you have 2 lone pairs, that's 2 peripheral atoms, and your molecular shape is bent again, although now the bond angle is closer to 109.5 degrees than it is to 120 degrees, as in the case of the bent molecule with the trigonal planar electron geometry.